Hello, this is our first video on Chapter 5, the Periodic Law. This unit begins with a history of the periodic table, which we learned about in the video we watched together in class. In Chapter 5.2, which is the topic of this video, we talk about electron configuration in the periodic table. And in Chapter 5.3, sections of which we will cover, we'll talk about electron configuration and periodic properties of elements. The periodic table is a chart that shows all the known elements, arranged in order of increasing atomic number, also arranged so that elements with similar chemical and physical properties are in the same vertical column, which we call groups or families. This is a manifestation of what's called the periodic law. The periodic law is a natural law that says that the chemical and physical properties of elements are periodic functions of their atomic numbers. Or, another way of saying that, is that properties repeat periodically when elements are listed in order of increasing atomic number. So if I took all the elements, all 118, lined them up in a big row, I would see that certain characteristic properties reoccur on a periodic basis, just like every seventh day is Wednesday. Now, a recurring theme in this unit is how the periodic table is related to electron configurations, which depend upon the electronic structure of the atom. So let's explicitly look at that. The question is, how is the length of a period in the periodic table related to the sublevels in the atom that are being filled in that particular period? Please get out a periodic table and look. In the first period, the sublevels that are being filled, only the 1s sublevel. There are two elements in the first period, hydrogen and helium. Why? Because we can only fit 2 electrons into the 1s sublevel. In the second period, from lithium to neon, we are filling the 2s and the 2p sublevels. How many elements are in that period? 8 elements. Why? Because we can put 2 electrons in the 2s sublevel, 6 electrons in the 2p sublevel. 2 plus 6 equals to 8. 8 electrons corresponds to 8 elements in the period. Same for the third period, except we're filling the 3s and the 3p sublevels. In the fourth period now, from potassium to krypton, we're filling 3 different sublevels. 4s, then 3d, then 4p. Why are there 18 elements in the fourth period? Because we can place 2 electrons in the 4s sublevel, 10 electrons in the 3d sublevel, and 6 electrons in the 4p sublevel for a total of 18 electrons, corresponding to 18 elements in the period. Likewise, in the fifth period, from rubidium to xenon, we fill the 5s, the 4d, and the 5p sublevels, another 18 electrons and 18 elements. In the sixth period now, don't forget, between lanthanum and hafnium, we have the lanthanides. So we fill, in order of complete filling, 6s, 4f, 5d, and 6p. 2 electrons in the 6s, 14 electrons in the 4f sublevel, 10 electrons in the 5d sublevel, 6 electrons in the 6p sublevel, for a total of 32. And likewise in the seventh period, from francium to oganesson, 7s, 5f, 6d, and 7p. So what we see is that the number of elements in a period is simply equal to the number of electrons that can fit into the sublevels that are being filled in that period. And don't forget why we can place a certain number of electrons in a sublevel. Any s sublevel consists of 1 orbital, so it can hold 2 electrons. Any p sublevel consists of 3 orbitals, so it can hold a maximum of 6 electrons. Any d sublevel consists of 5 separate orbitals, so it can hold a maximum of 10 electrons. And any f sublevel consists of 7 orbitals, so it can hold a maximum of 14 electrons. As a result of this, we often see the periodic table divided into blocks, and here they are. Those elements in groups 1 and 2 in blue are called the S block elements. Those elements in groups 13 through 18 in green are referred to as the P block elements. Elements in groups 3 through 12 are referred to as the D block elements. And the lanthanide and actinide series of elements that correspond to that are called the rare earth elements are called the F block elements. Where do the indications S, P, D, and F come from? Well, I hope you can see that the letter of the block refers to the sublevel into which that particular group of elements' last electron was added. So for example, the S block elements, groups 1 and 2, have their electrons put into an S sublevel, 2s, 3s, 4s, and so forth. Likewise, groups 13 through 18, the last electrons went into a P sublevel, and so forth. You'll notice that hydrogen and helium are not part of a block. Their electrons did go into the 1s sublevel, but because they do not share characteristics with the S block elements, all of which are soft and reactive metals, they are considered not to belong to a block. Here's a question. Which group of elements is called the noble gases, or the inert gases? You know that one, group 18. Why are they called noble gases? Well, you probably know because they're relatively unreactive. Why do they all have that property of being unreactive? Well, in chemistry, one of the themes in this unit is that you can very often answer a question about an element by looking at its electron configuration. So let's look at the electron configurations of the noble gases. Helium 1s2, neon has the configuration helium 2s2 2p6, argon has the configuration neon 3s2 3p6, krypton is argon 4s2 3d10 4p6, xenon has the configuration krypton 5s2 4d10 5p6. What do they all have in common? Well, you can see they all have completely filled S and P sublevels. Their outermost energy level, which corresponds to the S and P sublevel and the highest occupied principal energy level, is completely filled. So the noble gases don't need to gain, lose, or share electrons in order to be stable. Well, let's extrapolate further. This is simply one group on the periodic table, but we've got 17 other groups on the periodic table. Why do elements in the same group have similar properties? They all have the same number of electrons in the highest occupied principal energy level, or they all have the same number of, you know the word, valence electrons. Valence electrons are defined as the electrons in the highest occupied principal energy level, which are the outermost S and P sublevels. Why are valence electrons important? Because these are the electrons that are available to be gained, lost, or shared when atoms form chemical bonds. So the skill at this point is I give you any element on the periodic table and you count the number of valence electrons in the atom, and we will start with the electron configuration. So let's consider counting valence electrons for the elements in the second period on the periodic table. Lithium has the configuration helium 2s1. There is one electron in the outermost S and P sublevel, so lithium has one valence electron. Beryllium has the configuration helium 2s2. That's two valence electrons. Boron has the configuration helium 2s2 2p1, a total of 3 electrons in the highest occupied S and P sublevels, so boron has 3 valence electrons, and you see the pattern. As we move across the period, we are successively adding one more valence electron until we get to the noble gas, which has a completely filled S and P sublevel. 2 plus 6 is 8, so noble gases have 8 valence electrons. What about, say, iron, a D block metal? Well, its configuration is argon 4s2 3d6. If valence electrons are only those in the highest occupied S and P sublevels, then iron, and any other D block metal for that matter, will only have 2 valence electrons. And that's because when you're counting valence electrons, D and F electrons don't count. It's only the S and P. Now, let's talk about the concept of a group electron configuration. That is a generic electron configuration for all elements in a group and will represent the period by the principal quantum number n. So, for example, boron has the configuration helium 2s2 2p1. Aluminum has the configuration neon 3s2 3p1. Gallium has the configuration argon 4s2 3d10 4p1. Indium has the configuration krypton 5s2 4d10 5p1. What you see for each of these is that every element in group 13 has a completely filled S sublevel with 2 electrons in it and 1 electron in the P sublevel. And if it has a D sublevel, meaning if it's in the 4th period or lower, that's completely filled. So our group configuration for group 13 is NS2, N-1, D10, NP1, where N is the period number. Do you see how each of these electron configurations for the group 13 elements in periods 2, 3, 4, and 5 all have 2 electrons in the S sublevel. If there's a D sublevel, it's completely filled, and 1 electron in a P sublevel. So you should be able to write the group electron configuration for any group on the periodic table. So now let's finish up by taking a quick tour of the periodic table. We're going to go block by block and talk about some general characteristics of these elements. S block elements. Which groups and what elements? They include group 1, which we call the alkali metals, and group 2, which are called the alkaline earth metals. What are the group configurations of these groups? Very simple. All the elements in group 1 have the configuration ns1. All the elements in group 2 have the configuration ns2. And remember, n refers to the period. What are their properties? We saw this in the video on the history of the periodic table. They tend to be soft, highly reactive metals. What about hydrogen and helium? Well, hydrogen is 1s1 and helium is 1s2, but they're not considered to be part of the s block, as I said before, because their properties are very different. They're both gases, and helium is completely unreactive. The p block elements, which groups are these? Groups 13 through 18. What types of elements are found in the p block? Remember, if I ask you what type of element something is, there are 3 possible answers. And in fact, in the p block, you can find all types. There are metals. All the metalloids are in the p block, and most of the nonmetals are in the p block, all except for hydrogen and helium. There is an easy way to count the number of valence electrons of the p block elements. Group 13 has 3 valence electrons, group 14 elements have 4, group 15 has 5. The pattern is simply the number of valence electrons is equal to the group number minus 10. Why minus 10? Because we're subtracting groups 3 through 12, the d block metals. Their electrons don't count towards the valence electron count. There is an old-fashioned name for the s and p block elements, but I want you to know anyway. They're sometimes called the main group elements. Can we say anything generally about the properties of the elements in the p block? No, we can't. They're quite variable. We have noble gases that are completely unreactive. We have fluorine, which is an incredibly reactive gas. We've got some metals. We've got some metalloids. Quite variable. The d block elements, which groups? 3 through 12. What's another name for the d block elements? I'm not sure if I've used this term or not, but let's make sure we understand it. The d block elements or d block metals are synonymous with the transition metals. Maybe that's because you're transitioning from the s block to the p block. I don't really know. What are their electron configurations? They all have the configuration ns2, n-1, d, 1 through 10. So transition metals in group 3 will have 1 electron in the d sublevel. Transition metals in group 12 will have 10 electrons in the d sublevel, and they all have somewhere between 1 and 10. What are the properties of the d block elements? They're very typical metals. Iron, nickel, copper. When you think of a metal, hard, lustrous, malleable, conductive, you're probably thinking of a d block metal. Finally, the f block elements. Where are they? Remember, they're the ones we find in the 2 rows at the bottom of the periodic table, and we call them the rare earth metals or rare earth elements. Do they belong to a group? No. Remember, they are squished in between groups 3 and 4. Do they belong to a period? Yes, they do. They belong to periods 6 and 7. There are 2 series of F block elements. The lanthanides are in period 6. They follow the element lanthanum, number 57. And they include cerium, number 58, all the way to lutetium, number 71. And when we are in the lanthanide series, we are placing electrons into the 4f sublevel. The actinides, the second series of F block elements, are in period 7, following actinium, number 89. They include elements thorium, atomic number 90, to lawrencium, atomic number 103. And we are filling the 5f sublevel when we're in the actinide series. Many of the actinides are either synthetic or radioactive or both. Those that are not are relatively soft reactive metals, and they're very similar in properties to the metals in group 2. In our next video, we will talk about periodic trends and properties of elements and how we explain them using the periodic table and electron configurations. See you then.